Hello everyone, this is Eric. So in this presentation, we'll be looking at quantum cryptography and BB84 schema for key exchange. So before going into this, I want to give a small introduction on what is quantum physics and the history behind quantum physics in general. So before quantum physics was widely accepted upon, we were using something called classic physics. So all this physics was first introduced by Newton, and we all followed his rules into this new world basically. So Newton proposed that light was a particle. He believed that light was a particle. He made many theoretical explanation about it, many equations about it, but all of it was done on the assumption that light was a particle. And then there were many studies that followed his principles, and then there were studies that was stating that no, light wasn't a particle, it was a wave. So this duality, this confusion from scientists led to the discovery of something called quantum physics and quantum mechanics. So we are familiar with maths in a cryptography. Computer networks in general and computer network securities in general was all built on top of mathematical understanding of problems. So model arithmetic and all this stuff was the foundation blocks of cryptography in general. So quantum cryptography brought in physics into the mix. That's why I'm starting with physics, right? So as I was saying, what is quantum physics? Quantum physics is a branch of physics. It basically stated that smaller particles, it is applicable for smaller subatomic particles. This physics, this smaller subatomic particles, when laid together, form our world, right? So this phenomenon, this understanding of quantum physics led to the discovery of a lot of other stuff. It is still applicable in semiconductors, lasers, and a lot of other modern technology. So quantum physics is important for us to understand. So let me just give you a rundown on the most simplest and most basic concepts of quantum physics, and then we can go into what is quantum computing, qubits, and all other stuff. So let us start. Wave particle duality. This is something I was stating, right? So the entire concept of quantum physics and quantum mechanics in general started to be a concerning part of our physics when we try to understand light. Light was usually considered to be a particle, as I said. Newton considered it to be a particle. And then later on, a lot of studies supported the fact that light might be a wave. So one such study was Young's double slit experiment. So it basically proved that light was a wave. So if that's the case, then how does reflection happen, right? So reflection is when a particle hits something and comes back to us, right? So that must mean light is a particle. And Young's double slit experiment was basically there was two slits, so two layers of slits. In the first layer there was one slit, and the second layer there were two slits. So I've attached the photo right here for your perusal. Hope it's visible for you. So here you can see the light enters the first single slit, it then disperses, and then it enters the again two different double slits, and then it disperses again. So when this happens, what we would expect of light to be a particle is that it would go through the slits and then it will hit and then reflect back. But what we saw was patterns forming on the screen basically. They were high, they were low, they were high, they were low, they were high, they were low, which is visible in this image that I was attached. So this basically proved that wave nature of light and the particle nature of light was both existing. So we needed something to explain these phenomena. So we adapted quantum physics. So quantum physics basically stated light is both a particle and a wave at the same time. This is what wave particle duality means. So now we will go to superposition. Superposition is another interesting concept of quantum physics, which actually is really important for us to understand for us to go through quantum computing in general. So superposition basically implies a quantum particle is stateless. It can be more than one state. So let's assume I'm a quantum particle, right? So I'm here and I could be there. I can travel and I can be there. But technically, what if I could be both? You know, that's the concept behind superposition. So it's basically simply explained using qubits. So qubits is the computational particles. It's the most major computation units of a quantum computer. Before going into that, we are familiar with bits, right? Bits is what we are based on. So zeros and ones are bits, right? So our understanding of computation is all done through bits, KBs, GBs, and all these other stuff. So basically, a 0-1 computation model was built on top of bits. So a bit can be a 0 or a 1. These are the states of a bit. But for a qubit, it could be both. Until you observe a qubit, you will never be sure if it's a 0 or a 1. So that's the principle behind qubit. So it is both 0 and 1 at the same time. That is superposition. And entanglement. Entanglement is another really interesting topic. Uh, so basically, entanglement implies that two particles, no matter how far they are, could be related to each other. So if something happens to that one particle, will result in something happening to this particle. So let's assume me and my friend, right? So let's say I'm like miles apart from him. If something happens to me, it might affect him. I mean, not really, but technically in physics world. So let's say someone hits me. If he feels the pain, that is entanglement. We are entangled. So this particle insanity could define a lot of other physical phenomena. And uncertainty principle is one such phenomenon that we have to understand. So uncertainty principle was theorized by Heisenberg, right? So the theoretical physics aspect of it states that, so let's assume there's a free space and photons, the particle of light is there. It is moving, it is going here, there, it's reflecting off each other. So if we see that particle, if you measure that particle's position, we don't know its speed. If you try to measure the particle's speed, you don't know its position. So basically, in that free space, you find this photon, right? You manage to find it. You manage to locate the location of this photon, but you will be never be able to understand the speed of it. So if you try to measure the speed of it, you will never be able to understand the position of it. So this uncertainty brought into the measurement is what uncertainty principle is about. Since we're talking about measurement, let us go through measurement effect. So what is measurement effect? So this is also another major concept in quantum cryptography. This is how we basically detect intrusions in quantum cryptography. So measurement effect is basically when, let's say you find this proton, you are trying to understand its thing. You got this photon, you try to measure it, you try to find something to observe about it. If you observe it, that change in the particle can be measured a lot of it. It will set into one definite state basically. So this measurement effect will basically imply that if you see something, it will know. We can know if someone was on it basically. And quantum interference is very simple. Let us assume two quantum particles next to each other. They interfere with each other. They are not two independent particles. No matter how close or how far they are, there is some kind of interference that we can measure. So this would be how we find quantum particles. So these are the very basic concepts of quantum mechanics. So this will lead us to understanding what is quantum computing. So let us do that. Quantum computing. So quantum computing basically leverages all these physics phenomena within quantum physics to building computers. So let's assume there is this computer that I'm doing very hard computations on. Let's say it takes a month or so. Quantum computing has the effect to do that within seconds, within mere moments. That's how fast quantum computing is. This computational power is only possible through qubits, which I've stated are basically statelets. They are quantum particles that resemble something like a photon. So we basically assume these to be some kind of photon, and here you can clearly see how bits and quantum bits are different. So this is a simple explanation of what I just said to you earlier. So it's quantum computing is able to perform massive numbers of calculations. Even discrete logarithmic problems is one of the hardest problems that basically ensure the safety of cryptographic algorithms that we use currently. If that happens, it will break. For example, RSA, for example. If you take RSA, if you basically factorize these simple prime numbers, you'll be able to break the RSA. You'll be able to get the message. The intrusion will be possible. It's only not possible because it is not computationally feasible in today's computing world. But quantum computers can break that. Shor's algorithm proves that it can be broken. Grover's algorithm shows that it can be broken. Symmetric, asymmetric, no matter the cryptographic algorithms, it is possible to be broken through quantum. This is why NIST and all other stuff are trying to, come up with post-quantum cryptographic schemas and all these other stuff. There is a lot more to be discussed on that phenomenon. But right now, let us stick to quantum cryptography in general. So I've stated quantum mechanics, right? So how is it implemented in quantum computing? So these are just three examples of it: superposition, entanglement, and interference. So, so as I said, superposition, qubits can be zeros or ones at the same time, right? That implies that it's very, it's stateless. Zeros and ones aren't directly. So as I said, so let us assume these 001, 101, all these combinations are existing, right? But simply 3 qubits without changing its state can represent all of this at the same time. So which basically means you don't have to do that extra computation, right? So that proves that this is fast. Entanglement, as I said, when 2 qubits are entangled, their state remain linked no matter how far apart they are. So let's say this 1 qubit and this 1 qubit is there. You separate them, right? You try to understand 1 qubit, you'll be able to understand the other. That's what entanglement infers. So Einstein famously called it spooky action at a distance, which is a science story basically. Einstein, as we all know, is very important for physics in general, and his contribution to quantum physics and its adaptation is very important. Sorry for the little tangent there, but let us come back to our topic at hand. Interference. So interference is when the qubit states, the, everything within the quantum computing environment is all probabilistic, which means everything is measured in probability. It can be wrong, it can be right, it can be zero, it can be one. So let us assume this, qubit present. 50% of chance is that it will be a zero. 50% of chance is that it will be one, right? So that's basically what interference implies, that 2 qubits next to each other can change this probability of its existence. So let us now go to quantum cryptography. Quantum cryptography, as I was stating, is utilizing these quantum computers. This quantum technology and quantum physics, the basic concept using quantum physics is applied into our cryptographic, our computer networks world. This will make very big changes into our definite understanding of quantum and cryptography in general. So what is quantum cryptography? It is a method of secure communication that uses laws of quantum physics, right? It is able to protect data utilizing these quantum phenomena that we talked about. So quantum computing and quantum cryptography are kind of different from each other, as in quantum computing utilizes these on computing, quantum cryptography uses it as cryptography. So one such big phenomenon and one such big scheme that we use is quantum key distribution. So what is quantum key distribution? So let us assume a symmetric environment, right? So there is two keys. I mean, there is one key. There is two people, Alice and Bob. Both of us encrypt and decrypt the message using the same key. So I know the key, she knows the key. She sends the key to me. What if an intruder tries to get that key? That is possible, right? It is not, the key isn't really encrypted because I don't know the key, right? If Alice encrypts the key, I will never be able to find the key. So this is a schematic schema. So we need the same key to be distributed to each other. How would you do that without intrusion? That's the problem that quantum key distribution solves. So let us go to what is quantum key distribution. So quantum key distribution ensures that the key that I sent is secure. Okay. So there is two people. This is AES algorithm. Let's assume AES algorithm. You need 256 bits to communicate with each other. That is the key that you need. You need the same key. You need to distribute it among each other. How would you know this key is secure? How would you know there is an intrusion on a man in the middle? How would you know that? That problem is solved through key distribution. So this is a diagrammatic explanation of what is QKD. So you basically see there is two people, Alice and Bob. once it's on another important assumption that we have to clear right now is QKD is not used for encryption. It doesn't decrypt, it doesn't encrypt the data. It just distributes the key to the two people concerning or three people concerning, whoever may be. It basically is, we know Elgama, we know Diffie-Hellman key exchange. They basically are built on asymmetric models. The public, they basically create this common key so that they can communicate between each other. That's how these key exchange phenomena work. But this key distribution is completely different from one. It is symmetric, and another is that these keys are basically just distributed. They are not encrypted, they are not decrypted, they are distributed. Alice knows the common key, I mean the secret key, and Bob knows the secret key. Both of this both of this is built on top of encryption. Let's QKD is best for OTPs or one-time paths, I think. One-time paths are simple encryption using XOR gates or XNOR gates. But the implementation can be much more practical using AES or other symmetric schemas for encryption. So let's assume this is Bob, right? Bob sends a plain text. So this is Alice, right? So Alice sends a plain text to encrypt. It is encrypted using this secret key. And we send this to Bob through this channel. This is how it works. But QKD is different. So there is the classical channel that we send our data to. This is the actual encrypted data. And there is the quantum channel. Quantum channel is only for key distribution. So typically quantum data is traveled and distributed through the use of optical fibers. So optical fibers are the distribution channel through which these data is transmitted. So there is this optical fiber distribution channel, and then there is a classical distribution channel. This could be however you want. So this is much more of an hardware implementation of cryptography if you think about it. But let us go back a little bit. So Alice sends her encrypted data to Bob. Bob needs to decrypt it. He needs the key. Where does he get the key? Through the quantum channel. Quantum channel gives him the key. Quantum channel basically provides him the key encrypted. But what if an intrusion takes place? What if someone, let's say Eve, comes in and tries to get the key? If she gets the key, if she gets hold of the key, and if she gets hold of the message, she could decrypt it. She could take that message and send it back to Bob. So she will know the message. This will be active, passive, whatever attack it may be, she will know the message. For that, she must know the key. In order to find the key, she has to intrude the quantum channel. But quantum key distribution makes it impossible to do so. So one such way to do that is BB84. What is BB84? So BB84 is an encrypting schema that is used for QKD, and it is named after its inventors, Bennett and Brassard. They invented this back in 1984, and hence the name 1984. So BB84. So the pipeline of a common BB84 would be to sending this proton. Alice sends the proton. Bob receives the proton. They encode the key. So basically, this photon is polarized. Right? Polarization of light is very simple. Like, let's take for example a sunglass. Even a sunglass polarizes light. So polarization is very easy. Polarization basically implies changing the electrical field and magnetic field of a photon so that it can represent some value. To us, it's zeros and one. To a lot of other things, it could be various different things, positive, negative, and all of the stuff. So they send the photons as polarized photons, right? These photons are sent, received, and it's encoded. So it is encoded, the photons are measured, and they are able to, basically guess which is right through publicly sharing their basis. So what is basis? What is this? So we will see about this very quick. So this is the states of zeros and ones within the quantum systems that we are discussing right now. So 1 is represented as an upward polarized light photon, and 0 is represented as a vertical or more line of 0, which is a polarized light as well. So there are in superposition until someone detects it, someone intrudes, someone finds where it is. So that's a different topic, but they are in superposition, right? So they will pass through a filter. What is this filter? So basically Alice and Bob will have their own filters through which this light was sent. Let's assume you know, there is this water coming through a river. This river has two different filters. Alice and Bob have those different filters. Through these filters, the water gets passed through. From that, they will be able to find what the water was about. Is it a zero? Is it a one? So this is just for an example. So basically, these photons are passed through these filters. So BB84 proposes two different kind of filters, two different variation of these filters, which are rectilinear basis and diagonal basis. So what is this, right? So through an optical fiber, they are sending this polarized light. It goes through these filters and reaches the places that it needs to be. So the sender has their own filter, the receiver will have their own filter. The position of this filter might vary randomly. And as we all know, qubits are deterministic and it's probabilistic in nature. So they will have their own probability, so it will shift its own values based on this probability of distinction. So through a rectilinear basis, this one will pass through and it will go through a filter and one will be projected to the receiver. In a diagonal basis, a one will be in the diagonal. It will go through the filter and it will be presented to the receiver. This is how it will work. So what if these bases are different from each other? What if I have a rectilinear basis and they have a diagonal basis? They are sending a message to me and the one will be in a slanted way, right? How would I perceive that image? So let us assume this, there is this filter, there's this slit through which a photon is blasted. So if there is light on the other side, that's a 1. So if the filter is like this, there will be light. If there's a filter will be like this, a diagonal filter like this, it will also have a light. So how would I know the difference? How would this work? So this is how it would work. So Alice here sends Earth in a diagonal basis. Bob receives it in a rectilinear basis. So if that's the case, how would he discern the 0 and 1? So it is probabilistic in nature. It will shift. It will randomly shift. So when this is concerned, if you have bases like this, they are randomly chosen at random, right? So if both of them have a basis like this, they are cancelled out. We don't use those. It is wrong. That's how it works. So now we will see how transaction of this key takes place. So as I said, Alice will have his own basis and Bob will have his own basis. So this association, this arrangement of bases are different for both of them. They are randomly chosen as stated by this. Here you can see it's diagonal, it is rectilinear, it is diagonal, it is rectilinear, rectilinear. So there are same stuff here and there, right? So this will give them the proper output they need. If basis in this basis, Alice sends a 1, Bob will get the 1 properly. In this basis, if Alice sends a 1, he might get a 1, he might get a 0. It is probability, it is 50-50. It can be anything. So that will break the thing, right? So for our purposes, they are ignored. These, like, they are not same, right? So we don't really use them. Here you can see 1 is encrypted and decrypted as 1. Here 0 transmits as 0, 0 transmits as 0. But here we can see 1 transmits as 0. That is not possible. We cannot rely on a structure like this. You can see one is sometimes we can have the same transitions, but that doesn't mean it is applicable for every transitions. So different transition will imply different things happen. So this will be unreliable. So we only rely on this, right? This properly arranged basis. So how would they know the basis? How would they know this? These are randomly chosen, right? Alice and Bob choose their bases randomly. So how would Alice and Bob know that these bases this is the same basis as they have chosen for this transition? If that's the case, we can get the proper output. Other than that, it's unreliable output. So how would they know? They publicly share their bases. That's what happens, right? You can clearly see. So first they transmit this bits, random bits are transmitted, right? They then share their bases. This is basically the public key. This is not really the public key, but technically can be associated with public key, right? So they get the spaces, they find the spaces, and they compare their bases. So where is the proper basis? So, and then they assume that these bases are where the correct output is given. So for AES, we need 256 correct outputs to get the proper key. In order to do so, they transmit this n number of bits, right, to each other. Qubits are transmitted, n number of photons are transmitted between Alice and Bob till they get 256 common bases. These are randomly chosen, and they publicly share this basis, which is not really a problem because the major data, the key in and of itself is safe because Alice only knows the key, Bob doesn't yet know the key. They share the basis. If an intruder tried to get this basis, he finds this basis. It is not really a problem for the user. It is publicly shared. They only know what the key is transmitting. So when they publicly share this basis, both of them will know what basis, which bases are common. They don't change the basis. They know the common basis. So here, through the data sent at this common basis are reliable. So this 256 common bases are found. From that 256 common bases, they send the proper key. This is how key is distributed basically. So as you can see, Alice sends a rectilinear thing. If there is an intruder, let's assume Eve. Eve is trying to intrude this message. She doesn't know the basis at which they are transmitting this message. She doesn't know it. So when she comes in, she has to randomly chooses either a rectilinear or a diagonal. This random choice will bring in error to Bob because Bob knows this is not supposed to be correct or this is supposed to be correct. If that's the thing. So as you can see here, both of them are diagonal. So if one is sent here, Bob should receive one. After sharing their basis, they encode the key, they send the key, they get the key. Now the key is supposed to be 1 and 1. But now eavesdropper, Eve basically alters it to a diagonal polarized light. I mean, sorry, a rectilinear polarized light. So this is sent to Bob. This is wrong. Bob will find out. Bob will know, oh no, this is wrong. There's an intrusion. We have to stop this. The key is, taken apart. So they basically stop the thing. So this is how an intrusion is detected in BB84. So why is it not possible to intrude BB84? There are quantum physics phenomena that basically restrict this damn thing. We cannot make an intrusion on quantum computing. I mean, sorry, quantum cryptography and especially QKD BB84. We can never do that. Why is that? So in classic understanding of us, in classic physics, if there is a change, if you observe something, you will know that. That is the measurement effect that we discussed previously. So if Eve comes in, she observes this photon, the users, Alice and Bob, can able to find it. They will have some prolonged effect. This photon will get corrupted. You can see here, right? There's a 50% chance Eve will get the wrong basis. If that's the thing, if she gets the wrong basis, there's an error. In this error, they can find out. This is how intrusion is detected. So basically, the key, when the key is compromised, they will know. That's how this works. So there are a lot of physics phenomena that basically restricts the idea of intrusion. One such phenomenon is no cloning theorem. No cloning theorem implies that let's say you get this polarized photon, right? Eve gets this polarized photon. She intrudes this polarized photon. She tries to understand it. She doesn't know the basis. She somehow gets, you know, understands. Like we don't know the basis. It could be this or this. But she has to send it back to Bob, right? Without being detected. So if she has to send it to Bob, she cannot properly measure it. If she measured it, it will change. Right, that's the thing. So she has to either send the same copy again and then measure the different copy. That's how it can work. But you cannot copy it. You cannot clone a photon. That basically restricted by theorem and all. This is how quantum computing is quantum cryptography QKD theorem is able to basically provide us a safer way to distribute these keys, through a longer channel. So this was basically applied in a lot of other cryptographic methods. And recently, I believe Chinese satellite was able to apply something like this, a QKD, which was sent to another area, and they were able to get the key. But this is how it works. So as I was saying, how is this intrusion detected? So errors are introduced within this system. So when Eve comes in, Eve tries to encrypt the data. Eve tries to get the key from the channel. If that happens, she has to either choose a basis at random. If that happens, she has a 50% chance of failing. If that happens, Bob will get consistently bad, corrupted keys. So this is statistically understandable. So if there is 25% error rate, so it is, I think it is called quantum error factor or something like that. So if there is 25% quantum error factor within our key, we can understand that, this is bad. So why is that 25% error margin is given to that? Because this is photon. This is done through optical fiber. There could be noise in the data. We may never show. So we cannot, take noise as an intrusion. If that happens, we will be stopping the process for no reason at all. So that's why the statistical detection is important. So if that happens, just to make sure, there is a sacrifice through this process. Quantum key distribution basically implies they have to sacrifice some of its bits to known. So there is 256 bits, right? They take some of this bits, check with each other, Alice and Bob. So that means they basically share it and open. If there is more, there is it, the error rate, QB. If they finds it to be more than 25%, there's an intrusion. That's how it's detected. We know for sure there's an intrusion. This is how quantum computing works. This is how quantum cryptography works. This is how the detection is detected. And with that, I conclude my presentation. Thank you.